Okay, so picking up where we left off yesterday, we left off with J.J. Thompson's cathode ray experiment, and we learned that this cathode ray, basically was yanking negatively charged particles away from atoms, creating this beam of particles that were negatively charged. They bent or deflected toward positive charges, and we're able to measure that the ratio, the mass to charge ratio, was something of the order of 2,000 times smaller than hydrogen, which led him to believe that he discovered a piece of the atom, later called the electron. And of course, the plum pudding model is the model where we have this diffuse amount of positive charge surrounded by the particles. Okay, uh, right up until about 1910, 1911, it's around there exactly, 1910-ish, if I can say that. Ernest Rutherford, called the father of atomic theory. J.J. Thompson was called the grandfather, but again, he was the first to discover a particle of electron. Ernest Rutherford, okay, had a very famous and probably the most important of all the experiments, the gold foil experiment. And let me explain what happened here. Ernest Rutherford dealt with radiation. He actually first discovered two of the earlier forms of radiation, alpha and beta radiation. Okay, alpha, Greek for A, and beta for B, so thus A and B. Any case, what he had was he noticed that some metals gave off alpha particles, and we're going to learn later in the course that radiation is the work of metals that have unstable nuclei. They change their nucleus by doing something. And an alpha particle is a helium nucleus. And I'm going to tell you it's made of two protons, so I'll put those little P's in here, and two neutrons. We haven't defined them yet, and you've heard about them. So two neutrons, two protons are what an alpha particle is, and this comes right from a nucleus. So when I say an alpha particle, it's basically two protons, two neutrons coming from a nucleus of an atom. In any case, some metals give off alpha particles to make their nuclei stable, and we'll talk more about that. So we've got these alpha particles that are shooting out of this container, metal with a small opening to direct the charge. And this experiment was actually born out of some very eager undergraduate and graduate students who just wanted to do something around Ernest Rutherford. He was a god to a lot of people, and he became even bigger, if that's possible, after this experiment. So he actually gave this experiment to do. He was busy trying to study different forms of radiation, and at the same time they were studying the components of an atom. It was happening at the same time. In any case, he gave them a very thin gold foil, or very thin metal to shoot from. And he asked the students to sit in a room for about an hour to adjust their eyes. And basically what he had was a scintillator. A scintillator is an object, when hit, lights up. And before he put the very thin metal foil is just a very thin metal, he had the students sit, okay, Ernest Marston's Hans Geiger, sit and watch, okay, where these particles hit, and had them count the flashes. When a alpha particle, two neutrons, two protons, would hit the container, the container would flash, and they would count. So let's pretend, I don't know the actual data, but in 1 hour time, okay, after they sat in this dark room for an hour to adjust their eyes, let's say they counted 1,000 flashes. So for every hour, 1,000 alpha particles come out of this box, and that was a constant rate. Radioactive decay doesn't change over time, it's constant. So this would always be a constant number. So they came up with that. Okay, then they put, okay, this gold foil in its way. And lo and behold, when they recounted very thin, they got, let's say, 970, okay, hits. Okay, and so they lost 30. When they went up to tell Ernest Rutherford, okay, about this, they said, well, you probably did it wrong, so do it over and over again. They did, and they kept missing about the same number. So he suggested that they just move around to see where the others might be. So they spent hours, painstaking amount of hours, okay, and they just changed their position. So if they were looking right here, then they would look right here for an hour. Then they would look for here for an hour. And over time, by looking at the different positions, basically sitting in the dark with a magnifying glass, they found all 30. And what they found was, where were these particles? They found some beautiful deflections, some pretty amazing deflections, and even, this is most incredible, they found some uh, deflections that almost came directly back to the, I did this poorly, sorry. They, these, deflections, I should have circled the entire thing. These deflections almost bounced directly back, but those are far and few in between. So they really took, encapsulated, oh they encapsulated almost this entire object. I don't know what's going on here, but they basically encircled this metal sphere, and they were able to, again, spend painstaking amount of hours and look at every position, and they found all of the 30. Took hours because you can't just watch the entire screen. And what they found was some deflected, okay, and some actually bounced almost straight back. Okay, now of course the ones that bounced straight back were like 3 out of the 30 that missing. Most of the others were just deflections, and very few, went this far. Most of them, okay, went right through. Like 970 went right through without any changes in direction. Of the 30, some were major deflections, and some were even real major deflections that almost bounced straight back. So there were far and few between the ones that bounced straight back. Now, when they ran and told Ernest Rutherford about these results, supposedly the story goes that he dropped a piece of equipment that now was worth $1 million in his hands. His jaw dropped. And what he interpreted was that from this, he was able to discover something very important. If you look at the atoms, okay, remember, the gold foil is a few atoms thick. I'm just going to draw one. They expected everything to go through, okay? Because remember, the model of the atom was positives and negatives. Okay, the negatives were that plum pudding that were just haphazardly put in the atom, and the rest of the space, the interstitial space, was this, I don't know, glue of positives. So the positives were spread out over. So if you got something that has 2 protons, very positive. Now, they didn't know about protons. They just knew that the particle was very positive, and 2 neutrons. It's a pretty big particle. It should rip through this very diffuse, spread out matrix of positives. So we'd expect all of them to go through. Okay? But what really happened was, if I redraw the atom, or a very thin piece of atom, some of these deflected. Most of them still went right through, as we would suspect, but what we didn't suspect is these big deflections. And what we didn't suspect is the ones that almost bounced straight back. And the reason is because the entire mass of the atom was in the nucleus. And the only reason why these guys would deflect like they are is because the nucleus, where all the mass of the atom is, must have been positive. So we have a positive nucleus. So Rutherford discovered the nucleus of an atom. You say, what's so important about that? Well, it's important because you start arranging these things in a certain position. All of the mass of the atom was in the nucleus. And that mass included protons. Now, he didn't know about protons. He discovered protons a few years back, and neutrons were actually found about 30 or 20 years later or so. But neutrons and protons make up the entire mass of the atom. And electrons that J.J. Thompson discovered earlier, okay, were outside this framework and are in this empty space. Now, they don't take up mass of the atom because, remember, they're 2,000 times lighter than these guys, protons and neutrons. So for the first time, we're putting together a model of the atom where we have this nucleus, this very dense, thick nucleus. It's positively charged, and most of the atom must be just empty space where electrons are in. So let's go back to our drawing. So the Rutherford model, okay, is nothing more than having a nucleus filled with protons. That was discovered a couple of years back. And then, of course, 20 years later, we have the neutrons with electrons that are on the outside somewhere in that empty space. Okay, so this is now changing, okay, from this idea of a plum pudding to now a dense core called a nucleus. So what did he discover? He discovered the nucleus of an atom. He's actually to measure it. Now, how did he measure the actual distance? For probability. How many hits bounced off and the deflections and the angles. He was actually able to figure out the probability of deflections and angles to get an actual distance, which was, I believe, 1 times 10 to the negative 10 meters. Any case, he discovered a nucleus, but more specifically, he discovered that most of the atom is empty space where the electrons roam. Okay, and of course, he discovered that the nucleus is a dense, positively charged, and he knew it was positively charged because he was positive about it. No, because the deflections of this positive particle, he called an alpha particle, deflected away. We now know it's positive because of the 2 protons that make it positive. Okay, so it deflected away when it got close, like my drawing shows right here. So when a particle comes close, it would deflect away. If it got too close, it would bounce back. Now, those deflections were far and few between. Why? Because this is so small. The rest of the particles went right through. Okay, so he discovered that the atom is mostly empty space. The nucleus is positive, and the entire mass of the atom is a dense core where all the mass is located. So mass of atom is in this dense core. Okay, so important parts. Atom is empty space. The nucleus is a dense piece of matter. All the mass is located, and it's positive. So Rutherford's model, as I drew here the day before, I showed it was a nuclear model of an atom where you had most of the atom's mass and positive charge in a small part of the overall atom and most of the space. A very famous physicist made an analogy, said that if you take Yankee Stadium, put a baseball at second base would be the entire mass of the stadium, and the rest of the space in the stadium would be empty for electrons to be in. Now, Ernest Rutherford knew of electrons, didn't know how they organized, but were in their space somewhere, not just on the outside, as we talked about. Now, Ernest Rutherford, beyond finding the nucleus, he also found in 1918, okay, after the discovery of the nucleus, what he proposed for a long time, the proton. Now, the proton was coined by him. I believe it means the first. And the reason why it's named the first is because we knew of these canal rays. We talked about these tubes, the Crookes tubes, where you have an electron beam, let's say, going, oops, I don't know what was happening there. Electron beam was getting me. Let's go back. We had this electron beam shooting it this way. We also have positive ions shooting that way, which we called canal rays. When they used different types of gases, they eventually found the mass to charge ratio to be the smallest, to be of that of hydrogen. Hydrogen had the smallest whole number fixed ratio of these positive charges, and it led Rutherford to think, well, the first element fundamentally has 1 proton. And that's where it began. Now, his work in 1918 also led him to believe that a proton was a fundamental unit of charge, of positive charge in the atom. He noticed when he hit nitrogen, which has a mass of 14, and these numbers don't mean much to you right now, but they will, and 7, this is atomic number. If you take an alpha particle, which has a mass of 4 and 2 protons, so the bottom number is protons, top number is mass, Okay, what happened was it came together, and these are the first these are the first nuclear reactions. It made an 8 for oxygen. Oxygen has 8 protons, and 17 is its mass number. It also made a hydrogen atom, which has a mass of 1 and an atomic number of 1. Now we haven't quite gotten there, but these top numbers are the mass numbers, as we'll talk about in a second, and these bottom numbers are the proton numbers that we've talked about before. Now, who has mass? Now, Rutherford said the mass of the atom is locked up in the nucleus. Well, one of the things in the nucleus is protons. So if a neutron has 7 protons, this 14 is due to 7 protons. Now, of course, what's missing? Well, we'll talk about that in a second. But back to the reaction, he was finding through some analysis that when he reacted these alpha particles, which we now know are helium nuclei, into the nucleus of a nitrogen atoms that are found in most air, he was making oxygen and a very light element called hydrogen, and which was positively charged at this point. So it's the first element is made up of only one thing. So hydrogen without an electron, as we'll come to know, as 1 proton and 1 electron. And if it doesn't have an electron, it's just a proton. So he figured that hydrogen was made up of just 1 proton, so there was nothing left of it, and its mass was fundamentally 1 due to the 1 proton. So it led him to believe that he discovered the positive charge that kept the electrons in, that what's J.J. Thompson believed was stretched out toward the other atom. Remember, J.J. Thompson believed that positive was smeared all over, and these electrons just kind of were in that jelly, so to speak. Whereas Rutherford just said, hey, all the mass of the atom and its positive is in the nucleus, and he believes the particle was hydrogen. Proton meaning for first. And that's where the proton came from, 1918. Now, of course, he had some very important students that helped him, along with Hans Geiger and Ernest Marsden, who did the actual gold foil work. They had a name Henry Moseley, or H. Moseley, very important man in development of the atom. Okay, what did he discover? He discovered the atomic number. And you may say, well, didn't we already have that? Yeah, elements were listed in order. Hydrogen was 1, helium was 2nd, but they were just numbers we used to just order the elements according to how they were labeled on the periodic table. They didn't have any real significance. We knew of the proton existed, but we didn't know that this atomic number actually was a fundamental number of a proton. We didn't know that elements actually differed by their proton numbers. So what he did was, he did an experiment where he shot basically X-rays at very metal objects, and he saw their diffracting patterns, and I won't get into heavy detail. It's very much like the crystallography done with Rosalind to find a DNA structure, X-ray crystallography. But generally speaking, by hitting these X-rays on these metal objects when he first did it, the resulting wavelengths of light, okay, gave him an understanding of the energy. Now, what was happening, and again, we're getting before our time here, we have electrons that exist close to the nucleus. By giving the metal energy, these electrons are able to overcome the positive pulling force and jump farther away. Now, they eventually jump back, and when they jump back, they re-emit the energy in the form of X-rays. But these X-rays that gave off, okay, had different amount of energy based on how many protons were inside. What that means is, it takes, if you have 2 protons in a nucleus, well, these electrons will be attracted to these nuclei much stronger than with 1 proton. So he noticed the X-rays emitted, which represent the energy needed to break the electrons away, and the same energy for them to come back or jump back, were the same amount. Okay, and we'll talk more about that, but the X-rays that were emitted, the newer ones, okay, wound up being the square root of the frequency equal to the proton number. What he was seeing, very simply, to make this really seem very understandable, was that he was seeing whole number ratios of energy needed to pull electrons away from the nucleus compared to the number of protons. So when he figured out the energy, which is tied to the frequency and wavelength of all of this, we'll talk more about this. Once he found the energy,
my friends in chemistry, he realized that energy, okay, was some mathematical whole number to the proton number. And he was able to first start figuring out what the proton numbers of each element was. So he really discovered not really the protons, but he put on the map atomic numbers equal the proton numbers, and he rearranged the periodic tables that was put in order based on mass. Okay, and he rearranged them later a few times. And he was also predicted that there would be some new elements based on gaps in elements. Okay, I believe in 71, 72, there was elements that they didn't find yet that he said there was gaps where we should have another one there. So he found whole number ratios by using the mathematics, okay, of the energy it took to pull electrons away. Very simply, more energy it takes to pull them away, it must be due to more attractions or more protons. So very important. He went to war in World War I, and unfortunately, he died. They did not give posthumous Nobel Prize. They figured that he would have won one for sure if he continued. Now, Henry Chadwick, another important man that was also a student of Rutherford. Henry Chadwick, he was basically discovered the neutron. And Rutherford always postulated that neutron probably exists because they realized the alpha particle, which has a mass of 4 and a proton number of 2, they realized, oh, it's got 2 protons, but why is it twice as heavy as the number of protons? They thought possibly the nucleus had 2 protons and 2 electrons somehow that were adding the mass, but they realized the mass couldn't be that heavy, so that didn't work out. Henry Chadwick did a lot of energy evaluations that based on this very famous equation. Beryllium with a mass of 9, 4, plus an alpha particle was the particle of the day. Okay, when they bombarded them, you made a carbon nucleus with a mass of 12 and a atomic number of 6 protons, and it produced a particle that people did not know what to think of. It didn't have charge because people initially thought this was a photon or light, but they found later through the work of Henry Chadwick and his measuring his energies that this was in fact a neutron, a neutral atom that was adding to the mass of the nucleus. So the missing mass in an alpha particle was due to, okay, 2 more neutrons, I'm sorry. And Henry Chadwick found that a neutron, which had no charge, had a mass about the same as a proton, and that was the missing puzzle of the atom. So our atom, okay, has protons and it has neutrons, and we were able to, for the first time, figure out how many neutrons. Since the neutrons and the protons have about the same mass, this top number was able, which we already had since Dmitri Mendeleev in the mid-1800s, we were able to figure out what it meant. The mass of the atom, which we use for grams per mole, my friends, in chemistry, can now be used to evaluate, okay, how many particles. Here's 2 protons and then 2 more neutrons due to Chadwick's work because the neutron was about the same as a proton. And of course, he won a Nobel Prize for his work. And that's why they call Ernest Rutherford the father of the atomic model, because of the people that worked under him. So that's the basics of now we have a model where we definitely know now the protons. About Henry Chadwick, what I believe was 1932, and he actually was in a camp in World War I and was a prisoner as well. In any case, some important information. So now our model has the important protons by H. Moseley, the neutrons by Chadwick, okay, and of course our electrons. How they're arranged, we haven't gone there yet, but let's go to now being able to figure out how many of these particles are in atoms.
Okay, so this is table 0, okay, table O in your reference table. Okay, remember that alpha particle that Rutherford was shooting out? Well, there it's written in its notation, right there. Okay, and you notice it's a helium nucleus. Now the top number here is the mass number. Okay, and the bottom number is the charge number. So it has a mass of 4 and a charge of 2. Well, why? Well, the bottom number we also remember is the atomic number. So if you look at a proton, sometimes it has a hydrogen with it because hydrogen has 1 proton in it. That's why it has the atomic number 1. Now, if you notice, the top number is also 1. It has a mass of 1. So a proton has an atomic mass of 1 AMU. It's called atomic mass unit. It's not something we can measure, but it's a relative scale based on the boxes and everything that we've learned. Okay, we know that a mole of hydrogen is 2 grams. Okay, so therefore 1 hydrogen is 1 AMU. Okay, a neutron, and the word neutron is neutral. Look, it has a 0 charge, but it has a mass of 1. So we say that a neutron has 1 AMU. Therefore, neutrons and protons have the same mass. So, if I look back on a helium nucleus, if the charge is 2 or the atomic number is 2, I have 2 protons. How do I get neutrons? Well, if the mass is protons and neutrons, and this bottom number is the charge, or it's usually protons, you subtract it, you get neutrons. Bottom line is, I have a total mass of 4 and I got 2 protons. I have 2 neutrons. Okay. Now, believe it or not, a beta particle is the same thing as an electron. It used to be written here, and you should write it in table O, electron. An electron, look at that, has 0 mass. Now, that's not really true, but its mass is insignificant compared to these other particles. Why? Why? Because it's 2,000 times lighter. Its charge is -1. So there you go. You have your charges for your protons, neutral for neutron, +1 for a proton, okay, negative for an electron. And then you have the masses. Neutrons and protons have the same mass, electrons. All right, let's go to the periodic table. Okay, on top of your periodic table, you have this written on your periodic table. And notice they give you atomic mass number, goes on top. It's got a decimal place, we'll talk about that, the atomic number. So how do we get protons, electrons, and neutrons from an atom based on the Rutherford model? Well, we know that neutrons and protons have the same mass from table O. So this mass number that I have up here, okay, is telling me that I have some combinations of protons and neutrons that give me 6. This number we've learned already is the proton number. Atoms differ by proton numbers. So we learn that this has 6 protons. No other element has 6 protons other than carbon. Now, what you have to understand though is atoms are neutral. You say the word atom, it's neutral. So therefore the protons, which are positive, like from table O, equal the electrons that are negative to give you a 0 charged atom. Atoms are always electrically neutral. So if I ask you how many electrons in an atom, you would say 6. -6 and a +6 gives me 0. Neutrons are neutral from table O. But how do I get neutrons? Well, I know that these two, okay, right here, this one and this one give me the mass of the atom. Well, the mass of the atom is 12, but 6 of those 12s are protons. So to get neutrons, it's 12 minus 6. 6 neutrons. Okay? Now, that's in an atom. Atoms are always neutral. Okay? Now, these things right here are charges that the element loves to become when they become ions. So if you say ion, that means the atom has lost or gained electrons. A little preview as I'm running out of time is that if the carbon atom became -4 charge, became an ion, it would become -4 by actually gaining 4 more electrons, and that would be 10 electrons. Okay, and the reason why it's -4 is, well, carbon, okay, and I'm running out of space, but carbon going to carbon -4 is still carbon. So the proton number can't change, because you can become negative, you can lose positives, but we never lose the proton number because it's still the same symbol. Therefore, you gain electrons. So this has 4 more electrons than normal. So when it becomes an ion, and they list the type of ions it becomes, -4, when it becomes a -4 ion, it had to gain 4 electrons and have 10 electrons. Okay, so in any case, that's a little preview of where we're going.